So moving on. I think your next project is this week too. And it's a coding project. Your next project is this week. It goes, yeah, starts this week and it'll be doing 2 weeks.
Okay.
I think it's set to, it's probably already live, but you won't really be able to do it till Monday.
All right.
And it's a coding project. So lots of coding. It's going to be fun. This week we deal with approximations. So what does the derivative represent? Right, an instantaneous rate of change. Graphically, what is it? Slope of what? We call it that, but that's not really what it is. Slope of the tangent line. This leads us to being able to approximate certain values. So for instance, square root of 4.01. Using the derivative, we'll be able to approximate that value. Because we're using the tangent line to approximate, we call it a linear approximation. And the approximation is just the tangent line. We call it the linearization, or the linear approximation. We represent it as capital L of x. Ultimately, here's how it's working. Let's call that point A. And let's say we happen to know exactly what that value is. There's the tangent line. The idea is if you zoom in, really close to that point, the curve is approximately straight. Specifically, approximately the tangent line. So for points close to that A, we can just say, oh, well, it's just the straight line. And we know how to evaluate a linear function. It's very easy. So it would allow us to approximate what that value is, what that function value is. That's what's going on here. We also have what's known as the differential. Right, so suppose that y equals f of x is a differentiable function. We let d of dx be an independent variable that can be assigned any non-zero real number. Define the dependent variable dy as f prime of x dx. dy is called the differential for y. Again, be careful. Right? If y is f of x, then dy dx, the derivative of y with respect to x, is f prime of x, right? So it would seem that the differential is obtained by multiplying both sides by dx. Right? Because look how dy is defined. So it's almost like we did this, right? That is not what we're doing. Remember, d dx is an operator. While it kind of behaves like a normal fraction that we would think of, keep in mind that's not really what we're doing. If we say that dx represents the change in x, then the change in y is approximated as dy. And that's where you have to be careful. This approximation is only good if dx is small. It's the same argument here. would that tangent line approximation be any good here? Not going to give me a good value at all. The error is going to be insane. So the approximations are only good if your delta x, your arbitrary change, is really small, so really close to that point. Yes, I'm already in class. Go away. Now these are approximations. Whenever you do an approximation, there is always an associated error. Right. And then that brings in the idea of accuracy versus precision. They're not the same thing. Any kind of error analysis I'm going to leave for numerical analysis, which is a junior level math course. So we won't delve into any of the error analysis here. Just understand that there is an associated error with all of this. So we're going to approximate the value of 2.05 squared. So we want to use a linear approximation. What kind of function does that look like? Power function, specifically squared. Let's say f of x is x squared. What point is that really close to that we know the square of? 2. So we're going to set a to be 2. We're going to find the linearization of x squared at 2. That will then be used to approximate 2.05 squared. Well, we need f prime, right? What's f prime? 2x. At a, plus f of a is 4, right? It's 2 squared, plus 4 times x minus 2. There is our linearization. So 2.05 squared is approximately L of 2.05. .05 is the difference. 4 times 0.05 0.2. 2.05 squared is approximately 4.2. Now, how good was that? Well, that's all well and good, but we want relative. About 0.06% error. That's very good. Most acceptable errors are plus or minus 5%. We were at negative 0.06. Negative because we were actually at an underestimate. So it was actually a fairly good approximation.
Are we going to need to find our error percentage?
I'm just doing this for demonstration purposes. Now there is such a thing as a relative error that we do cover, but that's relative error when dealing with measurements, not finding the error of approximation. .1 cubed. It's a function. What's the function specifically? F of x equals what? What should A be? What's F prime? Evaluated at 5. And what's 5 cubed? There's the linearization. So 5.1 cubed is about 125 plus 75 times 0.1. What is 75 times 0.1? And 125 plus 7.5? So we have approximately 132.5 for 5.1 cubed. What did that water bottle ever do to you? So that's a 0.11% error. Which is, again, still pretty good. Square root of 24. What's the function we're using then? Technically, yes, but that's not how I'm going to write it. Square root function. And what should our A be? It's actually a really large delta x. Which is even worse. We'll see how this goes. Because that's actually a fairly large delta x. I mean, it's the only choice you have. I'm just saying it's a fairly large delta x. Which means this may not go well. What's F prime? What is it at A? Which I'll write as 0.1. F of A. There's the linearization. Root 24 would be about L of root 24. Oh, I'm sorry. That should be x minus 25, not 5. Negative 1. Right. Delta x is minus 1. And so we get about 4.9. I'm actually not terrible at all, 0.02%.
How'd you get negative 1?
Our x is 24, so 24 minus 25. And if you're using the linearization to ever approximate a value, you can always think of that last term, that x minus a, as delta x. How far away are you from your chosen x value? I still wouldn't use a power. Cube root. What's a? Let's hope that this goes as well as the last one did. What is f prime? What is that at 64? What is that as a decimal? We'll worry about that later. Right, L of x is cube root of 64 is what? 4 plus 148 times x minus 64. Cube root of 63 would then be about 4 plus 148 times minus 1. Four times 48. $196. Oh, I'm sorry, no, 192, you're right. Cube root of 63 is about 191 over 48. Whatever the hell that happens to be. Can't be bothered to find 1 over 48 by hand. Oof. 0.0208, repeating. Yeah, so hideous. So we'll use that as our value, 191 over 48. Now let's see how close we are. Guarantee this is going to give me something fun. I knew it, yep. Gives me something really sexy.
Is that good?
That is a sexy looking error. So how do I approximate? 2 ways to do it in Mathematica. You can do capital N, and then of what you want to approximate. Percent just means the last output. Or, let's put a decimal somewhere. Either way. That's about 0.003%. That's really good. Oh my God, if you just stick with the 2 decimal point rule for percentages, that's 0% error. That is really good. In fact, that is so good you'd get fired from government. Because it's too good. Government likes 50% error or more. Just look at their budget. My rest in peace. Sine of 3. What's F? What should we take for our A? Pi. What is F prime? At pi. I'm really watching for the exam.
Yeah, we'll see.
Means you may want to sit in a different seat. Wind up getting poked and hit, pushed off the seat. I'll be your witness for assault. Unless she pays me more. I'm not very loyal. I'm loyal to one thing and one thing only, and that's money.
Wow.
I can easily be bought.
say money is power.
Well, now you don't have to worry about it because she just made a pun. So I'll be your witness for free.
Oh.
What's wrong with puns?
Only I'm allowed to make them.
Forgot to think here. Crap.
What's sine of pi?
Zero.
There's the linearization, pi minus x. That means sine of 3 is approximately pi minus 3. Or 0.14. 0.14159.
Above our right-hand side of the equation, or at least the far right part of the equation, was x minus 1.
Was what?
On our linear function, yes.
It's x minus a.
Oh, well, I took the wrong thing written down.
So again, it's not going to give us the approximate value, it's going to give us an exact value. Ooh, that's our worst one yet. It's a 0.33% error. Even though our delta x was smaller than the previous one. What about e to the 0.1? It's f of x.
E to the x.
What should we use as our a? 0. F prime.
E to the x.
Evaluated at 0. F of a, 1 plus x minus 0. We wind up with just 1 plus x.
At the beginning, does it matter which value we assign to the Rx and which RA?
Yes.
It does?
Yes.
Okay.
Your a is the point that you're finding the approximation at. Right? So you want it to be a really convenient value, one that you know f of a.
No, I meant was, what if actually instead we set the e to the re of the x, and G approximated that as around 3 or something.
Made what x?
What if we made e x instead, and we left the 0.1 power as it was?
Well, since that's what you're trying to approximate, that really wouldn't serve any purpose. To wind up with about 1.1. What's another way I could say e to the 0.1? Tenth root of e. So I could also just use f of x to be the 10th root of x. Problem is, then I would have to find a value close to e that we know the 10th root of. 0 would probably be the closest. No, 1. 1 would be closer. 10th root of 1 is 1. I don't know what the next 10th root is, though. Be 2 to the 10th. What is that? Is that 1024? Or 512? Two to the 6th is 64. 7 is 128, 256, so does 1024. 1024 would be the next one, and that's way too far away from E. Worse yet, it's almost a whole half percentage error. That's unacceptable. You have a general idea of what's going on, right? Let's find some differentials. By the way, being able to find a differential is extremely important when we study integration. Just a heads up. dy, remember, is f prime of x dx. What is the derivative of that right-hand side with respect to x? This?
And the first parentheses. That's right.
dx. There's your differential for y.
And so how is this different than finding the derivative?
Because we're not finding the derivative, we're finding the differential. Theoretically, huge difference. In terms of actually calculating it, none.
Okay.
So then what would we use the differential for? That makes it different.
Approximating change in y. So if I wanted to say, there's our function. When x is 4, how does y change if I make x 4.5?
So you would just plug in your x.
X would be 4, dx would be 0.5. Delta y would be approximately that value there. So that's what dy measures. It's an approximation of a change in y. We can also use differentials to approximate relative error, which I'm going to get to. Find dy. Oh yes, my two physics people. This is going to be very important for you.
Two x times e to the 3x plus x squared times 3x times e to 3x.
What did you say it was?
I guess 3x.
No, it's the same thing. X squared times 3x is the same thing.
Dx.
Like that.
Would you put it all in parentheses, dx?
So that I definitely agree with. It's not 3x. It's just 3. So I'll just write that 3x squared. There's your differential. I think this stuff is also on the second exam. Unfortunately, so is related rates. And depending how the RNG gods feel, you may get a lot of related rates. You don't think I don't think I picked the questions myself, do you? I let RNG dictate that.
Could I provide my own RNG software that is not rigged at all?
Oh, it's not. Mine's not rigged. Mine's an actual publisher program.
I'm not saying yours is rigged, I'm just saying mine's definitely not rigged.
No, I will use the rigged one. nonsense.
I can hope, yeah.
Might throw in some quantum mechanics problems.
I don't think that.
Solve the Heisenberg's uncertainty equation.
What does that mean? What are you talking about?
Maybe have a string theory problem on there. And the final question, what is the meaning of life?
42.
There's actually an equation for that too, which is really funny.
There's an equation for the meaning of life.
Yes.
Can you teach us that?
Wait, let me see that sidebar.
I would really like to know.
I'm really curious. Isn't that hedonic calculus?
I don't remember. I just know there's an equation for life.
Oh, it's just something biological, isn't it?
I can draw this equation.
Maybe I'll throw entropy on the exam too. Entropy.
The trivia question from Who Wants to Be a Millionaire?
No, they're too easy. What is dy? This one's fun too.
Tan x plus 1 times 2 minus 2x. No, you talk. Secant squared. X. There we go. Oh yeah. Oh, someone else. Tan x plus 1 squared.
Like that.
With parentheses around it.
That.
No, don't do that. Don't do that. Just move it. Please. Hit the squared. And kick it out. Kick it out.
Yeah. No, I was
No,
saying.
delete the square, kick it out, bounce it.
That's good.
Yeah,
Is
just
that fun?
only hug the tan and the 1. No,
What?
just exclude 2.
What, 2 doesn't deserve a hug either?
No, absolutely not. It's too small. I have to personify that stuff.
It's too small.
Oh, my car was your car. Wait. Wait, so. Wait, you're in What is this? Parentheses around everything.
In this case, you actually don't need the parentheses. Because it's understood, because it's a fraction times something. Yeah, you're not wrong if you put parentheses around it, but you technically don't need them. The parentheses would avoid ambiguity, right? Because depending on how you write the dx, but typically in our math literature, we won't put parentheses around that. Questions so far? Just doing more of what we've been doing, right? Back to what we were doing before related rates.
Yeah. That right now.
Don't forget your project is due tonight if you haven't already turned it in. We'll continue this on Thursday.